Imagine a corner of the cosmos where the laws of physics twist into nightmares, where temperatures soar to millions of degrees, gravity crushes atoms into oblivion, and radiation lurks like an invisible predator. These aren't scenes from science fiction. They're real, terrifying places scattered across the universe, each more hostile than the last. Welcome to a journey through the top 25 most dangerous places in existence, locations so extreme they make black holes seem almost hospitable. Picture a realm where stars explode with the force of a billion suns, where magnetic fields strip electrons from atoms, and where entire galaxies collide in a dance of destruction. These cosmic death traps aren't just faraway curiosities. They're windows into the raw, unfiltered violence that shapes our universe. Think Earth's most extreme environments: volcanoes, deep sea trenches, hurricanes are deadly. They're playgrounds compared to what's out there. Take the heart of a quasar, where supermassive black holes spew jets of energy so powerful they could vaporize our solar system in seconds. Or venture near a magnetar, a neutron star with a magnetic field strong enough to erase your very molecular structure from thousands of miles away. Even the void between galaxies isn't safe. Dark matter and rogue black holes drift unseen, waiting to rewrite the fate of anything that strays too close. This isn't just danger, this is existence at the edge of annihilation. But why explore these cosmic killers? Because they hold secrets about how the universe began, how it will end, and the fragile thread that separates life from oblivion. By understanding these monstrous places, we unravel the mysteries of dark energy, the birth of elements, and the ultimate fate of reality itself. So brace yourself. Over the next 25 entries, we'll witness celestial horrors beyond imagination, each more breathtaking and more deadly than the last. The universe isn't just vast. It's vicious, and you're about to see why. The sun may seem like a familiar neighbor, a glowing orb in the sky that brings warmth and light, but step too close and you'll find yourself in the deadliest place in our solar system, the corona. This ghostly halo of superheated plasma stretches millions of miles into space, reaching temperatures of over 1 million degrees Celsius, far hotter than the sun's surface below it. Here, the laws of physics bend into chaos. Magnetic fields twist into monstrous knots, snapping like rubber bands and unleashing eruptions with the energy of a billion atomic bombs. Solar flares explode without warning, blasting radiation across the solar system at nearly the speed of light. Even more terrifying are coronal mass ejections, tsunamis of charged particles so massive they could swallow planets whole. If one struck Earth directly, our magnetic field would shudder under the assault. Power grids would fail, satellites would fry, and the delicate balance of life itself would teeter on the edge. But the corona isn't just a violent spectacle, it's a cosmic enigma. Why is this outer layer so much hotter than the sun's surface? Scientists still grapple with the mystery, probing the chaotic interplay of plasma and magnetism that defies conventional physics. Satellites like Parker Solar Probe brave temperatures that would melt steel, diving through this inferno to send back data, and each revelation only deepens the wonder. This isn't just a ball of fire, it's a churning, unpredictable force that reminds us even our own star is a place of unimaginable danger. From the sun's corona, we plunge into an even darker terror, a place where gravity wins forever. The event horizon of a black hole isn't just a boundary, it's the universe's ultimate point of no return. Cross it, and not even light can escape the crushing grip of spacetime itself. Imagine floating toward one, blissfully unaware of your doom until it's too late. The force on your feet would be millions of times stronger than on your head, stretching you into a grotesque cosmic noodle, a process scientists grimly call spaghettification. Your atoms would unravel like thread from a spool lost to the void. Yet black holes aren't just mindless destroyers, they're cosmic paradoxes. Thanks to Stephen Hawking's groundbreaking work, we know these monsters aren't eternal. They slowly leak energy, emitting faint quantum whispers called Hawking radiation. Over trillions of years, even the mightiest black hole would evaporate into nothingness. But don't mistake this for mercy. Get too close and time itself warps. A single minute near the event horizon could mean centuries pass elsewhere, stranding you in a nightmare where the universe ages without you. What lies beyond that dreaded edge? Physics breaks down. Einstein's equations shudder into nonsense, and matter is crushed into an infinitely dense speck, a singularity where our understanding ends. Some theories suggest wormholes or alternate universes might lurk there, but no probe could ever send back answers. Black holes are the universe's ultimate locked doors, hiding secrets we may never unravel. They remind us some forces are so vast, so ruthless, they defy comprehension. And they're out there right now, silently feasting on stars, bending light, and rewriting the rules of reality itself. If black holes are the universe's ultimate shredders, neutron stars are its cosmic anvils, crushing matter into forms so dense they defy reality. Imagine taking the entire mass of our sun and squeezing it into a sphere no wider than Manhattan. The result, a city-sized object so dense, a single sugar cube of its material would weigh as much as Mount Everest. But it's not just the mind-bending density that makes these stellar corpses deadly. Their surfaces are battlegrounds where gravity and magnetism reach apocalyptic extremes. Step onto a neutron star and you'll be flattened instantly by gravity 1 billion times stronger than Earth's. Your body compressed into a thin smear of subatomic particles. Even the atoms themselves can't survive here. Electrons are crushed into protons, forming a sea of neutrons so densely packed they behave like a single alien quantum fluid. And if the gravity doesn't kill you, the magnetic fields will. Some neutron stars, called magnetars, wield magnetic forces 1 trillion times more powerful than Earth. Get within 1,000 miles and those fields would rip the electrons right off your atoms, turning you into a cloud of ionized dust before you even knew what happened. But neutron stars aren't just silent killers, they're cosmic lighthouses. Many spin at dizzying speeds, blasting beams of radiation across space like interstellar strobe lights. These pulsars can rotate hundreds of times per second, their beams sweeping past Earth with such precision they rival atomic clocks, yet that rhythmic ticking is a warning. Those beams are torrents of X-rays and gamma rays capable of sterilizing entire star systems. In 2006, a magnetar 50,000 light-years away unleashed a gamma ray burst so powerful it briefly outshone the Moon despite being halfway across the galaxy. What's truly chilling is how common these monsters are. The Milky Way alone is littered with hundreds of millions of neutron stars, remnants of giant stars that went supernova. Some drift silently through the void, unseen until you're too close. Others orbit in binary systems, slowly devouring their stellar companions. And a few, like the infamous PSRJ 0737-3039, whip around each other at relativistic speeds, warping spacetime itself as they spiral toward a cataclysmic collision. These aren't just dead stars, they're ticking time bombs, each a reminder of the universe's capacity for violence on a scale we can barely comprehend. Rogue black holes are the universe's silent hunters, dark phantoms drifting unseen through the void, waiting to strike. Unlike their supermassive cousins anchored at galactic cores, these nomads wander untethered, propelled by ancient cosmic violence or the explosive deaths of their parent stars. Take Gaia BH1, lurking just 1,500 light-years from Earth. This invisible monster, weighing 10 times our sun's mass, betrayed its presence only by the frantic wobble of a star caught in its gravitational grip. No accretion disk glows around it, no jets scream into space. It's a shadow in the night, feeding only when unlucky stars stray too close. Galaxy collisions turn the void into a shooting gallery for these predators. Computer simulations show what happens when galaxies merge. Their central black holes may fling smaller ones outward like cosmic shrapnel. Some accelerate to thousands of kilometers per second, fast enough to escape their home galaxies entirely. These runaway behemoths then drift through intergalactic space cloaked in darkness. One could be sailing past right now, less than a light year away, and we'd have no warning until its gravity began twisting nearby stars like taffy. The terror of rogue black holes isn't just their invisibility, it's their unpredictability. A wandering monster could slip into our solar system unnoticed, its gravity perturbing orbits long before its presence becomes obvious. Neptune's trajectory might shift inexplicably. Comets could be yanked from the Oort cloud and hurled inward. By the time we saw stars stretching into spaghetti strands, it would be too late. Earth wouldn't be swallowed whole, we'd be torn apart by tides first, our planet's crust buckling under forces stronger than the moon's grip on our oceans. Yet these drifters also hold clues to the universe's most violent chapters. Some may be primordial black holes forged in the chaos of the Big Bang itself. Others could be remnants of quasars that flared bright in the early universe, then went dark. Finding them is like cosmic archaeology, each one a relic of destruction that shaped the cosmos. Telescopes hunt for the telltale flickers of stars suddenly brightening, their light bent by an invisible passerby's gravity. Every discovery peels back another layer of the universe's hidden architecture. One thing is certain, the galaxy is far from empty. It's a jungle, and we're only beginning to map the predators lurking in the dark. Magnetars turn the universe's volume knobs to 11 neutron stars so magnetically charged they rewrite the rules of physics. Imagine a magnetic field so intense it could wipe every hard drive on Earth from halfway to the moon. These cosmic monsters don't just bend the rules, they snap them in half. At their cores, magnetic forces reach a staggering 10 quadrillion times Earth's own, strong enough to twist the very fabric of spacetime into knots. Get within 100,000 kilometers, and those fields would destabilize the atoms in your body, turning you into a cloud of disassembled particles before you could blink. But magnetism is just the opening act. When a magnetar's crust, a lattice of iron nuclei under unimaginable pressure, shifts even a centimeter, the results are apocalyptic. The star's surface cracks like a frozen lake, releasing starquakes that ripple through space. These tremors unleash flares of X-rays and gamma rays so bright they outshine entire galaxies for milliseconds. In 2004, Magnetar SGR 1806-20 sent a pulse of radiation 50,000 light-years across space, temporarily distorting Earth's ionosphere despite being far outside our galaxy. The true horror lies in their unpredictability. Unlike pulsars with their metronomic beams, magnetars erupt without warning. Their flares twist magnetic field lines into braids of pure energy, accelerating particles to near light speed. These aren't just explosions, they're cosmic EMPs on steroids. A single outburst could sterilize planets light years away, frying atmospheres with radiation storms that make nuclear blasts look like firecrackers. Yet magnetars are also cosmic alchemists. Their magnetic fields are so extreme, they might transform photons into ghostly actions, hypothetical particles that could unravel dark matter's secrets. Some theories suggest their interiors harbor exotic states of matter, where quarks break free from neutrons, creating a soup of primordial chaos. Every flare, every ripple in their magnetic fields is a data point in humanity's quest to understand the universe's most violent corners. These stars are reminders the cosmos isn't just vast and beautiful. It's armed with forces so fierce they blur the line between natural wonder and cosmic horror. And somewhere out there, a magnetar is stirring, its next eruption already ticking toward inevitability. Hypernovas are the universe's ultimate fireworks, supernovas on steroids, unleashing energies so extreme they make ordinary star explosions look like campfires. While a typical supernova outshines entire galaxies for weeks, a hypernova cranks that violence up by a factor of 10. The difference scale. When a hypernova erupts, it doesn't just destroy a star, it obliterates it completely, collapsing into a black hole with such ferocity. It launches jets of plasma at nearly the speed of light. These aren't just explosions, they're directional death rays capable of sterilizing galaxies in a single blast. The real terror lies in what follows gamma-ray bursts. Lasting mere seconds to minutes, these bursts concentrate more energy than the Sun will emit in its entire 10 billion-year lifespan. If one struck Earth from even 5,000 light-years away, the gamma rays would rip apart our ozone layer, exposing every living thing to lethal ultraviolet radiation. The sky would literally glow with toxic nitrogen oxides, turning blue into brown. It's no wonder scientists suspect gamma-ray bursts caused at least one mass extinction, the Ordovician event 450 million years ago, wiping out 85% of marine life in a cosmic blink. NASA Fermi telescope has caught these monsters in the act. In 2022, it detected GRB 221909A, a burst so bright, it momentarily blinded Fermi's sensors despite originating 2.4 billion light-years away. Calculations showed its jet contained enough energy to boil Earth's oceans instantly had it been within our galactic neighborhood, and hypernovas aren't rare. Fermi data suggests one occurs somewhere in the observable universe every few minutes, meaning right now. A jet of pure annihilation could be slicing through some distant solar system, rewriting the rules of life before it even has a chance to evolve. What makes hypernovas so cataclysmic isn't just their power, it's their precision. Unlike supernovas that explode in all directions, hypernovas focus their fury into twin beams narrower than a laser pointer. These beams, powered by the newborn black hole's rotation, pierce through space like cosmic scalpels. Anything caught in their path is vaporized, anything just outside might survive, only to face a slower death from the shockwaves and radiation that follow. Yet hypernovas also forge the building blocks of life. Their furnaces create heavy elements like gold, platinum, and uranium elements ordinary supernovas can't muster. Every gold ring on Earth owes its existence to these apocalyptic events. They're destroyers and creators, sculptors of the periodic table even as they erase worlds. The universe doesn't just die with a whimper. Hypernovas prove it goes out with a scream, one so loud it echoes across billions of years. And somewhere out there, another monster is winding up for its final act. The Boötes Void isn't just empty space, it's a gaping hole in the universe so vast it defies explanation. Stretching over 330 million light-years across, this cosmic desert contains fewer than 60 galaxies where there should be thousands. If you placed the Milky Way at its center, the nearest major galaxy would be so far away. Our night sky would appear almost pitch black. No Andromeda, no Magellanic clouds, just an eerie void punctuated by faint, lonely specks of light. This isn't just a quiet corner of the cosmos. It's a structural anomaly so bizarre, astronomers initially doubted their own instruments. What makes the Boötes Void so unsettling isn't just its emptiness, it's the fact that it shouldn't exist. According to our best models of the universe's structure, regions this large simply can't form through normal gravitational clustering. Galaxies are woven into a vast cosmic web, connected by filaments of dark matter and gas. Yet the Boötes Void seems to have been carved out by some unseen force, as if a celestial knife had scraped away the stars. Some have speculated it could be the imprint of an ancient collision with a parallel universe, or the haunting remnant of a pre-Big Bang structure. Three-dimensional maps reveal the true scale of this enigma. While most cosmic voids are spherical, the Boötes Void is oddly shaped like a bubble warped by unseen pressures. Its few surviving galaxies huddle in thin, filamentary chains, as if clinging to the last threads of a shredded tapestry. One theory suggests these stragglers might be tidal debris, galaxies ripped from their clusters by gravitational forces we don't yet understand. Others propose the void isn't empty at all, but filled with dark matter so exotic it repels normal matter instead of attracting it. The implications are staggering. If dark energy, the mysterious force accelerating the universe's expansion, behaves differently here, it could rewrite our understanding of cosmology. Telescopes like the Sloan Digital Sky Survey have scrutinized the void's galaxies for clues, finding some that appear younger than they should be, as if star formation somehow rebooted in isolation. Could this place be a laboratory for unknown physics, a cosmic reset button? Then there's the eerie silence. The Boötes Void emits almost no radio waves, no ambient heat, just a chilling quiet that makes it the universe's ultimate ghost town. Some speculate advanced civilizations might deliberately avoid such regions, fearing the unknown forces at work. Or perhaps the void itself is a warning, proof that even the cosmos has places where the rules break down and darkness wins. One thing is certain, the Boötes Void isn't just a curiosity. It's a cosmic riddle challenging everything we think we know about how the universe structures itself. And as we peer deeper into its abyss, we're forced to wonder, is this an accident of nature or the signature of something far stranger? The Milky Way isn't drifting through space aimlessly. It's racing toward an unseen force at 14 million miles per hour, a gravitational behemoth so powerful it bends the paths of entire galaxy clusters like a cosmic puppeteer. This is the Great Attractor, a region of space roughly 250 million light-years away that defies everything we thought we knew about the universe's structure. Hidden behind the dust and stars of our own galaxy's plane, this invisible titan pulls thousands of galaxies toward it with a force that suggests the equivalent of tens of thousands of Milky Ways crammed into one space. Yet when astronomers first pointed their telescopes in its direction, they found almost nothing. Dark matter may hold the key. Current estimates suggest the Great Attractor's gravity stems from a concentration of mass nearly 100 quadrillion times heavier than our Sun, but visible matter accounts for less than 10% of that weight. The rest, an unfathomably dense knot of dark matter woven into the fabric of spacetime itself. Some theories propose this could be the heart of the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years, with the Great Attractor as its gravitational anchor. If true, we're not just being pulled toward a single point, but into a vast, spinning vortex of cosmic structure on a scale that dwarfs even the grandest galaxy clusters. But the mystery deepens. Recent observations reveal something even stranger lurking beyond the Great Attractor, an even more massive structure whimsically nicknamed the Dipole Repeller. This colossal void, nearly devoid of galaxies, exerts a repulsive force that may be helping push us toward the Great Attractor alongside its pull. Together, these two titans, one a gravitational magnet, the other a cosmic vacuum, act like opposing currents in an invisible river, shaping the motion of everything in our corner of the universe. The Great Attractor isn't just pulling galaxies, it's pulling back the curtain on the universe's hidden architecture. Infrared telescopes like the James Webb Space Telescope peer through the Milky Way's obscuring dust, revealing galaxies previously hidden in the attractor's grasp. Each new observation hints at deeper layers of complexity, from rogue black holes orbiting its core to filaments of dark matter stretching across millions of light-years. One day, we may find this isn't a destination at all, but a waypoint on a far larger journey, a single thread in the universe's grand tapestry of motion. Until then, its relentless tug reminds us even the cosmos is in flux, hurtling toward mysteries we've only begun to glimpse. Quasar jets are the universe's ultimate particle accelerators, blades of pure energy screaming across space at nearly the speed of light. Picture a beam of plasma so intense it could carve through entire star systems like a cosmic blowtorch, leaving behind nothing but ionized wreckage. Hubble's images reveal these monstrous structures stretching tens of thousands of light years, glowing with the energy of 1 trillion suns. At their cores lurk supermassive black holes, not just feeding on surrounding matter, but spewing out the leftovers with apocalyptic fury. What makes these jets so deadly isn't just their raw power, it's their precision. Unlike supernova that explode outward in all directions, quasar jets focus their energy into narrow, relativistic beams. The physics behind them is staggering. As matter spirals toward the black hole, magnetic fields twist it into a frenzy, channeling some particles into poles and accelerating them to over 99.9% light speed. These particles then slam into interstellar gas, creating shock waves that glow across the electromagnetic spectrum. One such jet, blasting from quasar 3C273, stretches over 200,000 light-years, longer than the Milky Way's diameter, yet remains razor-thin, a testament to nature's ability to concentrate destruction. The sheer energy defies comprehension. A single quasar jet can outshine its entire host galaxy, pumping out more power in seconds than humanity will use in 1,000,000 years. If one were to pivot toward Earth, the effects would be cataclysmic. Gamma rays and X-rays would strip our atmosphere, while the relativistic particles would bombard the surface like a nuclear shotgun blast. Even at distances of thousands of light-years, the radiation could trigger mass extinctions. Yet these jets aren't just engines of destruction, they're cosmic sculptors. By heating surrounding gas, they regulate star formation across galaxies, preventing runaway stellar births that could destabilize entire systems. Some theories suggest they even seed the universe with heavy elements, their shockwaves forging atoms far from traditional stellar furnaces. The Hubble Deep Field images capture this duality, jets both annihilating and nurturing. Their glow a beacon of chaos and creation. What's most unsettling is how common they are. Nearly every large galaxy likely hosted a quasar in its youth, and some, like Messier 87 with its now famous jet, remain active today. Their prevalence suggests that violence isn't an exception in the cosmos, it's the rule. These aren't anomalies, they're milestones in galactic evolution, reminders that creation and annihilation are two sides of the same coin. And somewhere in the depths of space, another jet is forming, its beam a silent scythe waiting to carve its mark across the universe. O-type stars are the universe's radiant executioners, blue-white behemoths so intense, their light alone can sterilize entire solar systems. Take Eta Carinae, a binary monster over 7,000 light-years away, pumping out 5 million times more energy than our Sun. Its ultraviolet radiation is so fierce, it strips atmospheres from planets light-years away, leaving behind barren cores. These aren't just stars, they're celestial blowtorches burning at surface temperatures exceeding 50,000 degrees Celsius, hot enough to boil titanium into vapor. Living near one would be a death sentence. The UV index on a planet orbiting an O-type star would make Earth's harshest deserts seem like shaded sanctuaries. DNA would unravel under the constant barrage of high-energy photons, making even the hardiest extremophile microbes impossible. But radiation is just the opening act. Stars this massive live fast and die young, their lifespans measured in mere millions of years instead of billions. Once their cores exhaust their nuclear fuel, they don't fade quietly. They detonate as supernovas or hypernovas, unleashing enough energy to outshine their host galaxies. Eta Carinae is already a ticking time bomb. In the 1800s, it underwent the Great Eruption, briefly becoming the second brightest star in Earth's night sky despite its distance. Astronomers now watch it closely, knowing its death throes could begin any millennium. When it finally collapses, the resulting explosion might bathe our planet in enough gamma rays to trigger a mass extinction, a reminder that even stars halfway across the galaxy can reach out with deadly consequences. Yet their violence serves a purpose. O-type stars are cosmic alchemists, forging heavy elements like oxygen and silicon in their cores. elements that will one day seed new planets and perhaps new life. Their stellar winds sculpt vast nebulas into stellar nurseries, triggering the birth of future suns. Even in death, their remnants, neutron stars or black holes, become gravitational anchors for new systems. These titans embody the universe's duality, creators and destroyers, givers of life and heralds of annihilation. And somewhere in the Milky Way, another O-type star is igniting, its brilliance a prelude to both cosmic violence and the possibility of rebirth. The heart of our galaxy isn't a place of gentle starlight, it's a maelstrom of violence where stars whip around an invisible beast at thousands of kilometers per second. Sagittarius A, the supermassive black hole anchoring the Milky Way, may seem dormant now, but Chandra X-ray Observatory's images reveal the truth. This monster is anything but asleep. Surrounding it stretches a nightmare landscape where newborn stars are torn apart by tidal forces before they can mature, where colliding gas clouds ignite brief, brilliant fireballs of X-rays, and where radiation levels are so intense they'd liquefy human flesh in microseconds. This cosmic arena defies imagination. 30,000 light-years from Earth, stars orbit Saga like moths around a flame, some so close they complete a full revolution in less than a human lifetime. One, designated S2, screams through its orbit at nearly 3% light speed, its path bent so severely by relativity, it traces a spirograph like rosette instead of a simple ellipse. The black hole's gravity doesn't just pull, it twists spacetime itself into knots, creating an environment where the laws of physics as we know them start to unravel. Yet the real danger lies in the invisible forces at play. Saga may weigh 4 million times our Sun, but it's a lightweight compared to active galactic nuclei. When it does feed, as it did in the recent past, the results are catastrophic. In 2019, astronomers witnessed a mysterious flare brightening its surroundings by 75 times in mere hours. Some suspect a rogue gas cloud was shredded into spaghetti. Its death throws lighting up the galactic center like a beacon. Other times, it may be snacking on asteroids or even entire planets, their final moments converted into bursts of high-energy radiation. The surrounding region, known as the Central Molecular Zone, is equally hostile. Here, gas clouds collide with the energy of supernova, forging bizarre molecules like ethyl formate, which, ironically, smells like rum but exists in concentrations that would poison any conceivable life. Cosmic rays accelerated by the black hole's magnetic fields bombard everything in their path, while protostars are yanked from their nurseries and hurled into the void at hypervelocity speeds. Some, like the infamous runaway star S5 HVS1, rocket outward fast enough to escape the galaxy entirely. What makes galactic cores truly terrifying isn't just their violence, it's their inevitability. Every major galaxy likely hosts such a beast, and Saga is actually one of the common ones. Yet even in its quiescent state, it shapes the destiny of our entire galaxy, its gravitational tendrils influencing star formation tens of thousands of light-years away. One day, when the Milky Way collides with Andromeda, Saga will merge with its counterpart in a cataclysm that will shake the cosmos, releasing gravitational waves powerful enough to ripple across the universe. Until then, it lurks in silence, a sleeping giant whose occasional twitches remind us the center doesn't hold, it devours. When neutron stars collide, the universe doesn't just witness a catastrophe, it undergoes alchemy on a cosmic scale. These cataclysmic mergers, known as kilonovae, are nature's most extravagant forges, where gold, platinum, and other heavy elements are born in the crucible of destruction. Picture two city-sized stellar corpses, each weighing more than our Sun, spiraling toward each other at half the speed of light. Their final embrace lasts milliseconds, but the aftermath reverberates across the cosmos, unleashing shockwaves, radiation storms, and gravitational ripples that rewrite our understanding of physics. The violence is unimaginable. As the neutron stars merge, their crushing gravity smashes protons and electrons together, forming neutron-rich matter that decays into precious metals. A single kilonova can produce hundreds of Earth masses worth of gold in seconds, enough to coat entire planets in a molten layer. But this wealth comes at a price. The collision sprays lethal gamma rays and cosmic rays in all directions, a death sentence for any nearby worlds. In 2017, LIGO and Virgo gravitational wave detectors caught such an event in action, GW170817, rippling spacetime from 130 million light-years away. The accompanying gamma-ray burst detected by Fermi telescope confirmed kilonovae as the universe's ultimate heavy element factories, yet the danger doesn't end with the explosion. The remnants of these mergers often collapse into black holes, their accretion disks glowing with X-rays as they devour stray neutrons. Others might form hypermassive neutron stars, short-lived monsters so dense they defy physics before inevitably imploding. Meanwhile, the ejected material expands at relativistic speeds, seeding the galaxy with radioactive isotopes that glow for years. Astronomers tracking GW170817's aftermath watched its debris cloud fade from blue to red as heavier elements formed in real time, a cosmic chemistry lab operating at temperatures surpassing 1 billion degrees. What makes kilonovae truly terrifying is their unpredictability. Unlike supernova, which announce their impending doom, neutron star collisions strike without warning. A merger within a few thousand light-years could bathe Earth in enough gamma radiation to collapse ecosystems, a silent assassin arriving at light speed. Yet these events also hold the keys to mysteries like dark matter and the universe's missing baryons. Their gravitational waves carry signatures of extreme matter states we can't replicate on Earth, while their light reveals how the cosmos redistributes its wealth. Kilonovae are the universe's most violent goldsmiths, destroyers, creators, and cosmic recyclers all at once. Every time you hold a gold ring, you're holding stardust forged in a cataclysm so powerful it warped spacetime itself. These collisions remind us the universe doesn't just create, it does so with unimaginable fury. Dark matter halos are the universe's ghostly scaffolding, invisible structures so massive, their gravity bends entire galaxies into submission. Picture a spiderweb woven from something we can't see, can't touch, yet outweighs all visible matter 5 to 1. These cosmic shrouds stretch millions of light-years across, enveloping galaxies like ours in a gravitational vise. Without them, stars at the edges of spiral galaxies would fly off into the void, their rotation speeds defying the laws of physics as we know them. But dark matter's grip keeps them anchored, its unseen fingers pressing down with the weight of 1 trillion suns. The true terror of these halos lies in their composition. We don't know what dark matter is, only what it does. It could be a sea of undiscovered particles, cold and sluggish, clustering in the cosmic shadows. Or something far stranger, theoretical WIMP, weakly interacting massive particles that pass through ordinary matter like ghosts through walls, or actions so light they behave more like waves than particles. Whatever it is, its presence is undeniable. Simulations show galaxies forming within these halos like pearls around grains of sand, their gravity sculpting the universe's large-scale structure over billions of years. But dark matter isn't just a passive observer, it's a cosmic puppeteer. In dense regions, halos can stretch and compress normal matter into horrifying shapes. Some galaxies, like the Bullet Cluster, reveal dark matter's handiwork in gruesome detail. When two galaxy clusters collide, their visible gas slams together and heats up, while their dark matter components pass right through each other, leaving gravitational fingerprints in their wake. The result, a nightmare funhouse of distorted spacetime where the laws of physics seem to twist in on themselves. And then there's the crushing gravity. At the heart of these halos, densities may reach such extremes that dark matter particles annihilate upon contact, releasing bursts of gamma rays. Some theorists suggest these regions could harbor primordial black holes, leftovers from the Big Bang, lurking unseen. Others propose dark stars might exist here, powered not by nuclear fusion but by the annihilation of dark matter itself. The most unsettling part, we're sitting in one right now. The Milky Way's dark matter halo extends far beyond its visible disk, its pull dictating the motion of everything from stars to satellite galaxies. Yet despite its omnipresence, it remains utterly invisible, a reminder that the universe's most powerful forces are often the ones we can't see. Until we unravel its secrets, dark matter will loom over us, shaping the cosmos in ways we're only beginning to fathom. Rogue planets are the universe's forgotten orphans, frozen worlds untethered from any star, drifting through the eternal night of interstellar space. Take PSO J318.5-22, a gas giant caught in James Webb's infrared gaze, glowing faintly with the residual heat of its violent birth. Without a sun to warm it, its surface temperatures hover near -260°C, cold enough to freeze nitrogen solid. Yet even in this frigid exile, these worlds harbor their own twisted forms of activity. Cryovolcanoes spew plumes of ammonia and methane instead of lava, freezing instantly into grotesque ice towers that shatter under their own weight. The origins of these wanderers are as mysterious as they are violent. Some may have been flung from their birth systems by gravitational slingshots, catapulted into the void during close encounters with sibling planets or passing stars. Others could have formed alone in the darkness, collapsing directly from rogue gas clouds too sparse to ignite into stars. Webb's observations reveal their atmospheres in unprecedented detail. Swirling storms of hydrocarbon haze, layers of exotic ices, and auroras crackling in magnetic fields untethered from stellar winds. These aren't just dead worlds, they're laboratories of alien chemistry where molecules chain together in ways impossible under the warmth of a sun. But the true horror of rogue planets isn't their loneliness, it's their invisibility. Current estimates suggest there could be billions drifting unseen through the Milky Way, outnumbering stars by a factor of 20. Their dark mass may even contribute to the galaxy's missing baryonic matter, warping the light of distant stars in fleeting gravitational microlensing events. One might be passing through our solar system right now, its gravity subtly perturbing the Oort cloud, and we wouldn't know until comets began raining inward. The most unsettling rogue planets might lie in the galactic halo, where temperatures approach absolute zero. Here, theoretical Steppenwolf planets could host subsurface oceans kept liquid by tidal forces or radioactive decay, a last refuge for life in the abyss. Venturing there would be a one-way trip into darkness, where the only light comes from the feeble glow of decaying isotopes or the occasional flash of a methane geyser. Rogue planets remind us that the universe's definition of a world is far broader and far stranger than we once imagined. They're ghosts of failed systems, nomads of the void, and perhaps even accidental arcs carrying the frozen seeds of life between the stars. Wolf-Rayet stars are the universe's ultimate cosmic shredders, raging beasts in their death throes, literally blasting themselves apart with winds so fierce they could strip a planet to its core in hours. Imagine a star so unstable, it hurls its own atmosphere into space at 5 million miles per hour, creating a hurricane of stellar material visible across galaxies. These aren't just dying stars, they're celestial suicide bombers, tearing themselves to pieces long before their final supernova detonation. Hubble's images reveal their chaos in vivid detail. Vast, glowing nebulas shaped like hourglasses, where the star's ejected layers collide with interstellar gas in violent shockwaves that glow across the electromagnetic spectrum. What makes Wolf-Rayet stars so terrifying is their rarity and violence. Representing less than 1% of massive stars, they've burned through their hydrogen fuel at breakneck speed, exposing their superheated helium cores. Surface temperatures soar beyond 100,000 degrees Celsius, so hot They emit most of their light in the ultraviolet range, invisible to human eyes but lethal to anything nearby. Their spectral signatures tell the story: broad emission lines of ionized helium, carbon, and nitrogen, evidence of nuclear fusion products churned to the surface by relentless convection. These aren't the tidy absorption lines of normal stars, they're the jagged fingerprints of a star in freefall. The solar winds unleashed by these monsters defy comprehension. Every second, a Wolf-Rayet star like Gamma Velorum ejects 1 billion times more mass than our Sun's entire solar wind, enough to sculpt entire nebulas like the Crescent Nebula in Cygnus, where stellar material rams into slower-moving ejecta at relativistic speeds. These winds carry more kinetic energy than a supernova explosion spread over centuries, a slow-motion detonation that peels away the star's outer layers like an onion. Some Wolf-Rayets lose an entire sun's worth of mass in just 100,000 years, a cosmic blink of an eye, but the true horror lies in their fate. Every Wolf-Rayet star is a supernova waiting to happen, and when they go, they don't fade quietly. Their stripped cores collapse into black holes or neutron stars, often triggering gamma-ray bursts that could sterilize nearby star systems. Some, like the infamous WR104 in Sagittarius, are so close to the edge, astronomers debate whether they've already exploded. Their light just hasn't reached us yet. Others, like the binary system VFTS 682 in the Tarantula Nebula, might skip the supernova entirely and collapse directly into black holes with barely a whimper. Wolf-Rayets are more than just stellar oddities, they're the universe's heavy element factories. Their winds blast carbon, oxygen, and nitrogen into the interstellar medium, seeding future generations of stars and planets. Every breath you take contains atoms forged in these violent furnaces, their legacy woven into our very biology. These stars are a reminder: creation and destruction are inseparable in the cosmos, and even in death, the universe's most violent objects shape the story of life itself. The Large Hadron Collider doesn't just push the boundaries of physics, it sparks nightmares of Earth being swallowed by microscopic black holes. When this 27-kilometer ring beneath the French-Swiss border smashes protons together at 99.9999991% light speed, the energies involved are mind-bending. For a fleeting instant, conditions mimic those just after the Big Bang, with temperatures exceeding 100,000 times the Sun's core. Theoretically, that could create quantum-scale black holes, fleeting distortions in spacetime so tiny they'd evaporate before your next breath. Yet headlines love to imagine these specks growing unstoppably, consuming our planet from the inside out. The truth: Earth gets bombarded by particles with far higher energies every second from cosmic rays, and we're still here. CERN safety protocols read like a physicist's version of a disaster movie script, except every doomsday scenario has been debunked by hard math. The key lies in Hawking radiation, the faint glow predicted to emanate from black holes as they lose mass. Any micro-black hole created in the LHC would be so small, it would vanish in a puff of quantum particles before harming a single atom. Even if Hawking's theory were wrong, and decades of observations suggest it's not, the LHC's energies are pitiful compared to cosmic collisions happening naturally in Earth's atmosphere. Ultra-high-energy cosmic rays have struck our planet with the force of a baseball pitched at 60 miles per hour, packing way more punch than anything humans can manufacture. If these could spawn killer black holes, astronomers would have spotted the evidence in ancient rocks or lunar samples by now. But the LHR team didn't just rely on theory. Before smashing their first particles, they commissioned multiple independent safety reviews, each concluding the same thing: nature's already run this experiment countless times. The universe is essentially a giant particle accelerator, and Earth's been in the crosshairs for 4.5 billion years without incident. Even stranger, some theories suggest micro-black holes wouldn't just harmlessly evaporate. they might pass through Earth like ghosts, their gravitational pull too weak to interact meaningfully with normal matter. The real marvel isn't the imagined apocalypse, it's what the LHR has actually achieved. By recreating conditions unseen since the universe's first trillionth of a second, it's uncovered the Higgs boson, probed quark-gluon plasma, and hunted for dark matter particles. Those tiny, hypothetical black holes, they could be clues to extra dimensions with gravity leaking into our universe from higher spatial planes. Every time the beam activates, it's not just testing physics, it's testing the limits of human curiosity. And that's a risk worth taking. The Virgo cluster isn't just a collection of galaxies, it's a cosmic pressure cooker, where the space between stars bubbles with gas hotter than the sun's core. XMM Newton's X-ray vision reveals a nightmarish sea of plasma reaching temperatures of 10 million degrees, a roiling expanse where atoms are torn apart into subatomic shrapnel. This isn't empty space, it's an invisible inferno stretching across 15 million light-years, so energetic it glows in high-energy X-rays visible only to space telescopes. What makes this intergalactic furnace so lethal isn't just the heat, it's the density. Though the gas is thinner than Earth's best laboratory vacuums, its sheer volume means it outweighs all the cluster's galaxies combined. Wander into this region, and the plasma would bombard you with particles moving near light speed, stripping away your molecules layer by layer like sandblasting flesh off bone. Even stars aren't safe. Galaxies plunging into the cluster, like the hapless spiral M87, get ram pressure stripped, their star-forming gas ripped away by the plasma's relentless drag, leaving behind ghostly trails of stolen materials stretching hundreds of thousands of light-years. XMM Newton's spectral data reveals the gas's gruesome composition: ionized iron, oxygen, and silicon forged in supernova and blasted into the void by galactic winds. These elements glow at specific X-ray wavelengths, painting a map of violence that traces the cluster's history. Some regions show shock fronts where galaxy subgroups collided, heating gas to record temperatures. Others harbor bizarre, cold fronts, sharp edges where cooler gas clumps plow through the hotter medium like icebergs in a boiling ocean, the most unsettling discovery. The gas shouldn't exist. At these temperatures, theorists predicted it should have cooled and settled into galaxies eons ago. Instead, supermassive black holes at the cluster's core act like cosmic radiators, pumping energy back into the system through jets that stir the plasma like spoons in a cauldron. Without this feedback loop, the Virgo cluster would have collapsed under its own gravity long ago. This swirling plasma ocean is more than a celestial curiosity, it's a warning. As the Milky Way hurtles toward the Virgo cluster at over 1 million miles per hour, astronomers watch with morbid fascination. In a few billion years, our galaxy will plunge into this superheated maelstrom, its gas reserves evaporating like morning dew in a blast furnace. The stars will survive, but their birthright, the raw material for future worlds, will be lost forever to the cluster's insatiable hunger. The universe doesn't just create and destroy. It slow cooks. Thorn-Zitkow objects sound like something ripped from a theorist's wildest daydream, stars so bizarre, they defy conventional stellar physics. Picture a red supergiant, its bloated outer layers stretching hundreds of millions of kilometers. But lurking at its heart isn't a fusion engine, it's a neutron star. This cosmic cannibal swallowed its binary companion, leaving the dense corpse to orbit inside its new host like a parasitic core. The result, a ticking time bomb where two stellar extremes wage war under one photosphere. These hybrid monstrosities aren't just theoretical. HV 2112 in the Small Magellanic Cloud bears all the hallmarks of a Thorn-Zitkow object: overabundances of lithium, molybdenum, and rubidium, elements forged in the neutron star's extreme environment and dredged up to the surface by convection currents. Artist renditions of such objects reveal their surreal anatomy. Imagine a red giant's turbulent plasma threaded with magnetic tendrils from the embedded neutron star, its radiation distorting the outer layers into grotesque asymmetrical bulges. One side might glow hotter where the neutron star's gravity focuses energy, while the other fades into a cooler, stretched-out haze. Inside, the conditions border on apocalyptic. The neutron star's crushing gravity disrupts the red giant's core dynamics, creating a turbulent soup of nucleosynthesis unlike anything in normal stars. Hydrogen from the surrounding envelope rains down onto the neutron star's surface, triggering runaway nuclear reactions that could detonate unpredictably. Some models suggest these objects end their lives in hypernova on steroids, their neutron cores spiraling inward until they collide with the red giant's collapsing core, producing a gamma-ray burst that could sterilize nearby star systems. Yet for all their violence, Thorn-Zitkau objects might be cosmic alchemists. Their unique interiors could synthesize rare heavy elements like gold and platinum in quantities dwarfing ordinary supernova. Every time astronomers spot unusual chemical signatures in a star's spectrum, they wonder, is this another hiding a neutron star in its belly? The hunt continues, with telescopes scouring stellar populations for other candidates like HV 2112. What makes these objects truly unsettling is their stealth. From the outside, they masquerade as ordinary red giants. Only subtle chemical fingerprints betray their true nature. One might be shining in our galactic neighborhood right now, its hidden neutron core biding time before the inevitable detonation. In a universe full of obvious dangers, Thorn-Zitkau objects remind us sometimes the deadliest threats were the prettiest disguises. Rising from the Milky Way's core like spectral chimneys, the Fermi bubbles stretch 25,000 light-years into space. Twin lobes of gamma radiation so vast they dwarf our entire galaxy's visible disk. Fermi LAT's all-sky maps reveal these eerie structures in stark detail, faint yet unmistakable, glowing with the energy of a long-forgotten cataclysm. Unlike the delicate filaments of supernova remnants, these bubbles are brutish and symmetrical, their razor-sharp edges suggesting they were forged in a single explosive event rather than gradual processes. What cosmic detonation could have left such scars? The leading theory points to Sagittarius A, our galaxy's supermassive black hole. While quiet today, evidence suggests it was an active quasar just a few million years ago, a blink in cosmic time. As it devoured surrounding matter, twin jets may have blasted outward perpendicular to the galactic plane, their relativistic particles inflating these colossal structures like balloons. The energy required staggers imagination, equivalent to 100 supernova detonating simultaneously. Even more unsettling, the bubble's gamma rays aren't just leftovers. They're actively produced today as high-energy electrons collide with starlight, a process called inverse Compton scattering that Fermi's detectors capture in real time. But the violence didn't stop there. X-ray observations reveal the bubbles are wrapped in shock fronts, vast ripples where the outflow slammed into intergalactic gas at millions of miles per hour. This collision zone, dubbed the Fermi haze, crackles with synchrotron radiation as magnetic fields whip particles to near light speed. Whole star clusters near the bubble's edges show abnormal motions, their orbits permanently altered by the ancient blast wave. Some astronomers speculate this event might have triggered a flurry of star formation along the bubble's rims, as compressed gas clouds collapsed under the pressure, a cosmic silver lining to an otherwise apocalyptic phenomenon. The timing adds another layer of mystery. Geological records show Earth experienced a minor extinction event 2.5 million years ago, right when these bubbles likely formed. Could radiation sleeting through the galaxy have affected our planet? While unproven, it's a chilling reminder that black holes don't just shape their immediate surroundings. Their tantrums echo across tens of thousands of light years, rewriting the histories of stars, planets, and potentially even life itself. What lingers most hauntingly is the silence. Unlike active galactic nuclei with their screaming jets, the Fermi bubbles emit no sound, just a faint, persistent glow that whispers of violence past. They're tombstones for an era when our placid galactic center was a beacon of destruction, and perhaps a preview of eruptions yet to come. As telescopes probe deeper, each new dataset peels back another layer of this cosmic onion, revealing just how dynamic and dangerous even a quiet galaxy like ours can be. The Sloan Great Wall doesn't just stretch across the cosmos, it distorts it. This colossal filament of galaxies, spanning 1.4 billion light-years, is so massive that its gravitational pull warps the very fabric of spacetime around it. Imagine a spiderweb woven not from silk but from entire superclusters, each containing thousands of galaxies, all threading together into a structure so vast it would take light, the fastest thing in the universe, 1.5 billion years to travel from one end to the other. Discovered in 2003 by the Sloan Digital Sky Survey, this behemoth is one of the largest known structures in existence, a cosmic skeleton so immense it challenges our understanding of how matter should be distributed in the universe. What makes the Sloan Great Wall so terrifying isn't just its size, it's the way it bends reality itself. Einstein's theory of relativity tells us that mass warps space-time, and this filament has enough mass to twist the paths of light from background galaxies like a funhouse mirror. Astronomers call this effect weak gravitational lensing, where the wall's gravity subtly distorts the images of galaxies behind it, stretching them into faint, ghostly arcs. The SDSS data reveals this distortion in stark detail, mapping the invisible gravitational field like ripples in an unseen pond. If you could stand beside it, an impossible feat, the sheer weight of its galaxies would bend time, making clocks tick slower near its core than at its fringes. Yet even more unsettling is the mystery of how such a structure could form. According to cosmological models, the universe shouldn't have had enough time since the Big Bang to assemble something this colossal. The Sloan Great Wall defies the so-called cosmic homogeneity scale, a theoretical limit on how large structures should grow before gravity's pull is counterbalanced by the universe's expansion. Some theorists speculate it might be evidence of exotic physics, perhaps dark energy behaving differently on vast scales, or relics of primordial quantum fluctuations amplified beyond prediction. Others suggest it's not one continuous wall at all, but a chance alignment of smaller structures, a cosmic illusion woven by our limited perspective. The wall's sheer scale also raises existential questions. Galaxies within it are so far apart that even at light speed, communication between them would take hundreds of millions of years. Civilizations born in one section could rise and fall long before their light ever reached another. And yet, despite the distances, the wall's gravity binds them together in a delicate dance, a reminder that the universe is far more interconnected and far stranger than we once imagined. As telescopes like the James Webb probe deeper into these cosmic megastructures, each new observation peels back another layer of the Sloan Great Wall's secrets, forcing us to rethink not just the universe's architecture, but its very rules. This isn't just a wall of galaxies, it's a gravitational monument, a relic of forces so immense they sculpt the cosmos on scales we're only beginning to comprehend. And somewhere in its shadow, our Milky Way drifts a speck on the tapestry of something far grander and far more mysterious than we'll ever fully grasp. Deep in the crushing atmospheres of Uranus and Neptune, the universe cooks up a storm unlike any other, a hail of diamonds, at pressures exceeding 1 million times Earth's sea level and temperatures hotter than the sun's surface. Methane, the same gas that fuels your stove, shatters into carbon atoms, which then crystallize into glittering diamond shards. These aren't tiny specks. Scientists estimate some could grow to the size of icebergs, sinking through slushy layers of ionic water and compressed hydrogen like celestial buckshot. The first lab experiments recreating these conditions left researchers speechless. In 2017, Stanford's SLAC National Accelerator Laboratory blasted polystyrene, a methane analog, with high-powered lasers, watching as X-ray snapshots revealed carbon atoms rearranging into diamond structures in nanoseconds, proof that this surreal phenomenon isn't just theoretical. It's happening right now, over 2 billion miles away, but the horror of diamond rain isn't just its extravagance, it's the physics behind it. Neptune's mantle, where this occurs, is a fluid nightmare. Here, water molecules break apart into oxygen and hydrogen ions, forming superionic water, a state where oxygen crystallizes into a solid lattice while hydrogen ions flow through it like electrons in a wire. This bizarre conductive soup generates the ice giant's freakishly strong magnetic fields, which wobble drunkenly off-axis and flicker unpredictably. The diamonds themselves aren't pristine gems, but ragged clusters contaminated by hydrocarbon goop, tumbling through this electrified sludge until they eventually settle near the cores, forming layers that might resemble Earth's mantle if our planet's interior were laced with a billionaire's ransom. What makes this spectacle truly unsettling is its scale. Uranus and Neptune may be called ice giants, but their interiors are more like chemical pressure cookers. Some models suggest their cores could harbor vast diamond seas, molten carbon studded with solid diamond icebergs, churned by convection currents hotter than lava. The energy released by sinking diamonds might even fuel these planets' vicious winds, which howl at over 1,000 miles per hour despite having almost no solar heat to drive them. It's as if the very act of carbon crystallizing into gems whips the atmospheres into frenzy. Then there's the dark twist: these diamonds will never be mined. They're trapped under thousands of miles of supercritical fluid, doomed to cycle through the planet's layers for eons until perhaps Neptune's eventual death scatter them into space as cosmic debris. The universe's most opulent storm rages forever in the dark, unseen and unreachable. Yet it teaches us something profound. The same carbon in our bodies, in every living thing, might elsewhere in the cosmos be compressed into glittering stones. A reminder that the line between life's building blocks and celestial treasure is thinner than we think. Lab experiments continue to push further, using advanced X-ray diffraction to study how diamond rain might behave in even more extreme exoplanets. Each discovery peels back another layer of these alien worlds, proving that the universe's imagination outshines our wildest fantasies. Neptune and Uranus aren't just blue marbles floating in space. They're alchemists' crucibles, turning methane into diamonds with the casual brutality of a universe that never stops surprising us. The Big Bang singularity isn't just the starting point of our universe. It's the ultimate cosmic no-go zone, a realm where physics itself ceases to function. Picture all the matter and energy in existence compressed into a point of infinite density. A mathematical abstraction so extreme that even spacetime loses meaning. This isn't just a black hole's crushing grip scaled up. It's a breakdown of reality's very framework, where the laws of thermodynamics, relativity, and quantum mechanics all collapse into screaming incoherence. The cosmic microwave background, that faint afterglow from the universe's infancy, is our only window into this unfathomable moment. A snapshot of the cosmos just 380,000 years after the singularity, when the fog of plasma finally cleared and light could travel freely. Yet the CMB's serene glow hides unimaginable violence. Those subtle temperature fluctuations, variations of just 1 part in 100,000, are the echoes of quantum chaos magnified to cosmic scales. During inflation, the universe expanded exponentially in a fraction of a second, stretching microscopic quantum ripples into the seeds of galaxies and voids. But rewind further and the equations fail. General relativity predicts infinite curvature at the singularity, a state where uncertainty reigns and even causality might unravel. Some theories suggest gravity itself could become repulsive under such conditions, triggering the Big Bang like a cosmic coiled spring. Others propose the singularity never existed, that our universe is a four-dimensional membrane colliding with another in a higher dimensional bulk, or that time loops back eternally in a cycle of bounces. What makes the singularity uniquely terrifying is its inevitability. Black holes offer an event horizon, a warning before the point of no return. The Big Bang singularity had no such buffer. It was everywhere at once, the entirety of existence trapped in a state beyond comprehension. Even theoretical tools like loop quantum gravity or string theory, which attempt to smooth out the singularity's infinities, only push the mystery back one step. Was there a before? Did time emerge from timelessness? The CMB offers no answers, its primordial light frozen at the edge of our observational horizon like a veil drawn over the unknowable. And then there's the haunting implication. If our universe began in such a state, could it happen again? Some models of dark energy suggest a future big rip, where the cosmos tears itself apart down to quantum scales, a chilling symmetry of creation and destruction. The singularity isn't just a relic, it's a reminder that the universe's most fundamental truths might always lie just beyond our grasp, shrouded in the very conditions that made us possible. The deeper we probe, the more questions arise. Satellite missions like Planck have mapped the CMB with exquisite precision, yet every refinement reveals new anomalies, cold spots, improbable alignments, asymmetries that hint at physics beyond our models. Perhaps these are scars from the singularity's aftermath, or fingerprints of a multiverse we'll never see. One thing is certain, the Big Bang's ground zero remains the ultimate cosmic danger zone, not just for its unfathomable energies, but for the existential vertigo it induces, the realization that our entire reality is built on a moment that defies understanding. The universe doesn't just contain dangers, it began with one. Vacuum decay sounds like science fiction, but it might be the universe's ultimate reset button, a catastrophic event where the very fabric of reality unravels at light speed. Imagine a bubble of false vacuum suddenly forming in space, a region where quantum fields don't quite sit at their lowest energy state. Like a pencil balanced on its tip, the universe's current vacuum is metastable for now, but one nudge away from collapsing into a truer, lower energy state. If that happens, the laws of physics as we know them could rewrite themselves in an instant. Inside this bubble, fundamental constants like the speed of light or the strength of gravity might change. Atoms could dissolve, their binding forces altered beyond recognition. The shockwave would expand at light speed, erasing everything it touches: planets, stars, galaxies, leaving behind a new reality governed by alien physics. The scariest part, we wouldn't see it coming. A vacuum decay bubble could already be racing toward us from some distant corner of the cosmos, and by the time it arrives, it would be too late to even process the end. Theoretical physicists sketch this scenario using quantum field theory diagrams, mapping the energy landscape of the universe like topographers charting a mountain range. Our current vacuum sits in a valley, a local minimum, but somewhere deeper, a truer vacuum might lurk. Quantum fluctuations could, by sheer chance, tunnel through the energy barrier separating the two, sparking the bubble's formation. Once it begins, there's no stopping it. The bubble's walls would be a boundary between existence as we know it and something else. Strangely, vacuum decay isn't entirely hypothetical. Particle colliders like the Large Hadron Collider briefly create conditions where vacuum stability could be tested. So far, the vacuum holds, but every high-energy experiment nudges the pencil slightly, probing whether it might tip. Some theories even suggest that dark energy's accelerating expansion could make the universe more susceptible to decay over time, turning the cosmos into a ticking time bomb. Yet vacuum decay isn't just doom and gloom. If it's possible, it hints at a multiverse where different regions of space operate under different physics, some barren, some teeming with life under entirely unfamiliar rules. Our universe might be one fragile configuration in an infinite tapestry of possibilities. Until we understand quantum fields deeply enough to rule it out, vacuum decay remains the most unsettling existential threat of all. Not an explosion or collision, but reality itself folding into something unrecognizable without warning and without mercy. The Omega Point isn't just an ending. It's the universe's final whisper, a distant epoch where time itself becomes meaningless. Picture a cosmos so stretched thin by expansion that every star has burned out, every black hole has evaporated, and the temperature of empty space barely hovers above absolute zero. This is heat death, the ultimate victory of entropy, where no energy gradient remains to power even the faintest flicker of life or light. Galaxies, once vibrant with billions of stars, are now nothing but scattered particles drifting endlessly apart, their distances so vast that not even photons can bridge the gaps. The universe doesn't just fade, it forgets, its structure dissolving into a featureless void where nothing happens forever. But heat death isn't the only possible finale. Some models suggest a far more violent conclusion, the Big Crunch. If dark energy weakens or reverses, gravity could claw everything back together in a cataclysmic reversal of the Big Bang. Galaxies would accelerate toward one another, their light blue shifting as space contracts. Temperatures would rise until the cosmic microwave background itself becomes an oven, roasting any surviving matter. Eventually, all structure collapses into a singularity, a fiery mirror of the universe's birth. The irony is cruel. A cosmos born from a singularity might return to one, erasing every galaxy, every planet, every memory of existence in a final, crushing embrace. The terror of these scenarios lies in their inevitability. Entropy always increases, and even the most intricate structures, from DNA strands to galaxy clusters, are temporary eddies in a relentless current toward disorder. Simulations show protons themselves might decay over unimaginable timescales, reducing all matter to a sea of leptons and photons. Quantum fluctuations could spark brief, Boltzmann brains, isolated consciousnesses flickering into existence by sheer chance, only to vanish again in the dark. Yet the Omega Point also holds a strange beauty. In the far future, the universe's expansion might stretch wavelengths so long that the last light ever emitted, the final flickers of dying stars, will redshift into undetectability. The cosmic timeline will freeze, with no observer left to mark its passage. Time, as we understand it, will cease to have meaning. The universe won't so much end as forget how to begin again. These aren't just abstract theories, they're reminders of our place in the cosmic story. Every act of creation, every star born, every civilization rising, all are fleeting against the backdrop of deep time. The Omega Point is the ultimate equalizer, the silent horizon toward which all things march. Whether through icy silence or crushing fire, the universe's finale is already written in the laws of physics. Our only defiance is to witness, to learn, and to marvel while we still can. From the sun's corona to the crushing depths of black holes, from rogue planets wandering the void to the diamond hailstorms of ice giants, we've journeyed through 25 cosmic nightmares where the laws of physics twist into horrors beyond imagination. These aren't distant threats, they're reminders that our fragile existence hangs by a thread in a universe overwhelmingly hostile to life. Every gold atom in your jewelry was forged in a neutron star collision. Every breath you take contains oxygen blasted from a supernova. We are stardust, yes, but stardust shaped by violence on scales that humble even our greatest achievements. Yet here's the paradox, the same forces that could obliterate us also made us possible. Without hypernova, there'd be no heavy elements for planets. Without the Milky Way's supermassive black hole, our galaxy might never have formed. These cosmic monsters aren't just destroyers, they're the architects of reality itself, the chaotic crucible where chance and necessity collide to create islands of order like Earth. That's the awe hidden in the terror. We're here because the universe is dangerous. So what do we do with this knowledge? We keep exploring. Every telescope pointed at the Fermi bubbles, every probe diving toward the sun, every equation scrawled about vacuum decay, their acts of defiance. To study the void is to stare into the abyss and say, "I see you," and perhaps one day to understand, "Now it's your turn." Which of these cosmic horrors chilled you to the bone? Do rogue black holes lurking unseen keep you up at night, or is it the eerie silence of the Boötes Void? Share your scariest space theory in the comments, because the universe is vast, mysterious, and far stranger than fiction. And together we'll keep unraveling its secrets, one terrifying discovery at a time. The cosmos may be indifferent to our existence, but that just makes the fact we're here to witness it all the more extraordinary. The universe doesn't care if we're afraid. But we should never stop being curious.